So we've already created a formulation for the confidence interval for a population proportion. What the point of this video is to show you a second alternate formulation of the confidence interval that looks a little bit different than the confidence interval that we came up with in class. So to that end, let's start by considering a function. So we've got this function h of p, which is going to be our p hat minus p, quantity squared, minus z squared sub alpha over 2 times p times 1 minus p over n. So don't worry about where this function came from for right this second. Just this is our formula, our function that we're going to be considering for this development. Recall that our p hat here is our sample proportion, so our y over n. Same idea as what we had in class. All right, so we can rearrange this a little bit if we multiply out the binomial and distribute the fraction, and then refactor. We get this quadratic expression in p. So we've got that 1 plus z squared over n times p squared. We've got a minus 2p hat plus z squared over n times p, and then plus a p hat squared. The idea for this right now is that we want to find out where this quadratic is equal to 0. So we use the quadratic formula, solve it for p. And of course, just our ordinary quadratic formula, the minus b plus or minus square root of b squared minus 4ac all over 2a, just plugging it into the quadratic formula. And then let's do a little bit of simplifying here. First, all I did was just rewrite the fraction. I split it up over the plus minus sign. And then in the first term, just cancel out a 2. Of course, if I try to factor a 2 out of the top, I need to put a 2 in the denominator in the second piece. That's why we've got over 2n there. And then here, this is just multiplying out the binomial and distributing over the sum here. Notice under the radical, your 4p hat squareds cancel. In every single term, there's a z squared. So we can factor out that z squared. Also notice that the first and the second term here and the last term have a 4 in it, and a p hat in it. So if I factor out the 4 and the p, factor out the 4, and then I can write it as p hat times 1 minus p over n for that first part. And then the z to the 4th alpha over 2 becomes a z squared because we've already factored out a z squared. So square root of z squared, of course, is just z. Because again, remember our z sub alpha over 2 is going to be the positive one here. And so we can simplify to this. Also, we could, the last part here is I took the 2 out of the denominator here, and taking the 2 in the denominator would make it a 4 on the inside of the radical. So that's why this 4 is gone, canceled out, and then we have over 4n squared here. So that's just a moving of this 2 under the radical. All right, so this looks messy, and we talked at all about why we want to do this, but these are the zeros for this quadratic function. So keep that in mind again. These are the zeros for this quadratic function. Okay, don't worry so much about the simplification. All right, so we still want to construct the 100 times 1 minus alpha % confidence interval. So in this case, we still want this exact same expression, right? We want the distance between our sample population proportion and the actual population proportion to be less than or equal to some z sub alpha over 2, the actual distance between those two things. We want that probability to be 1 minus alpha. Well, notice that if I multiply by the radical on both sides and square, well, actually first I squared both sides and then multiply on both sides and simplify, notice that I get this expression that looks very, very similar to what we had on the last slide. In fact, the left-hand side of this inequality is h of p. So when rewriting the inside of this probability statement, like we had in class, doing it a little bit differently, giving it a little bit of a different approach, we've come up with this now quadratic expression that we want less than or equal to 0. We want that probability to be 1 minus alpha. All right, it's a quadratic function, and if we go back to the quadratic function, we'll notice that that first term was the 1 plus z squared over n. That's certainly going to be positive. So it's a positive leading coefficient on the quadratic function. So in order to have the quadratic function be less than or equal to 0, we need the p to be in between the two roots. So that means that our confidence interval is just take those two zeros that we found in that on the first slide and make those the endpoints of our confidence interval instead. Now, granted, this doesn't look very nice, okay, but it is a different way to get at the confidence interval for a population portion. It's going to be slightly different than what we saw in class. However, one of the things that we notice is that all of these things that look like nasty fractions, the z squared alpha over 2 over n, and the same thing for over 2n, and the same thing for 4n squared, if n is big, which is what you would typically do if you're taking a sample to try to get, say, polling data, you're going to have large n. These will all be really close to 0. Look what happens when you put those things close to 0. You're left with p hat in that first term here, right? Because these are going to be zeros. You're going to be left with a 1 here, and this will be 0. So you're left with z sub alpha over 2 times the square root of p hat times 1 minus p hat all over n. It's the same confidence interval that we got in class if you put zeros in for those. So when n is large, you get approximately the same confidence interval as when we had in class. It's a different confidence interval, but it's approximately the same if n is large. We didn't do the same thing for confidence intervals for means, because if you do this, you could do the exact same approach if you do this for means. If you form a quadratic, find the zeros, turns out you get the exact same confidence interval. You don't get something different. So that's why we didn't do that in our previous formulation of the confidence intervals. All right. So we'll talk about a third possibility in class as well. So we'll talk about that after you've had a chance to watch this video.